Hey everyone, welcome back to another episode of our Route to Conquering Acid-Base Equilibra series. My name is Sean, I'm a tutor from Inkie, and I'm bald, not by choice. And so today we'll be moving on to level 3 out of 5 of our Acid-Base Equilibra series. For those who have been keeping up with us, we have already gone through the three definitions of acid and bases in level 0. And also in level 1, we have already found a way to calculate the pH of strong acid and bases, as well as calculating the pH of weak acid and bases in level 2. So for those who have yet to watch these videos, you can feel free to click the link on top in the right hand corner right now. And if not, today our little Mario will be moving on to level 3 of our series, which is finding the pH of salt hydrolysis and more importantly, understanding the concepts behind salt hydrolysis. So if you're ready and I'm ready, and let's move on. Yay. So just a quick overview of what salt hydrolysis means. Salt hydrolysis is essentially defined as a reaction in which ions in a salt react with water to produce an OH- or H3O plus ions. So who's the main character in this topic or in this subtopic is basically a salt. So when you guys think of salt, what do you guys usually think of? You guys perhaps could be thinking of the common salts that we find in our practical, for example, our sodium chloride or potassium chloride. And usually these salts, you will not really think them of being acidic or basic because they are indeed neutral. But later on, if as we dive deeper into the topic of acid-base equilibria, as well as future topics such as periodicity, we will realize that some of the anions or cations in salts are actually capable of causing solutions to become acidic or basic when dissolved in water. Alright, so just an overview, these are essentially the three conditions in which a cation or anion is capable of undergoing salt hydrolysis with water. So I would like you guys to pause this video right now and you can just jot down in your notebook in these three conditions. So although maybe you guys may not be able to understand it at the moment, or you guys might find it a bit confusing, like what does these conditions even mean? Rest assured, each of these pointers will be covered as we move on to the later slides. So before we move on to each of the conditions that are mentioned in the previous slide, let's take a break and go back to level 2 of our weak acid and base. I'd like us to think a bit deeper in which that definition of a weak acid or base. What causes a weak acid or base to actually dissociate partially in water to give a low concentration of H plus or OH minus ions? And secondly, I'm not sure if all of you are familiar with this relationship between a strong acid weak conjugate base or weak acid strong conjugate base kind of relationship. I would like you guys to also ponder why is that the case. So to answer the two questions in the poster in the previous slide, let us have a little inquiry test whereby we have two different kind of acid, a weak acid which is ethanoic acid and a strong acid which is our commonly known hydrochloric acid. Let's see how they perform when they dissociate in a beaker of water before them. By only focusing on the forward reaction of both reactions, we see that both weak and strong acid in this case perform as a Bronsted acid, in which they donate a proton to water, which is the conjugate base for both reactions, and as a result giving H3O plus ions or H plus ions as we most commonly know it. So by only focusing on the forward reaction, we see that both weak and strong acid actually perform the same way. But now, what differentiates or what distinguishes a weak acid from a strong acid? Let's pay attention to the backward reaction. Focusing on the left hand side of the slide, we have ethanoate as our conjugate base. And back in organic chemistry, we know that the ethanoate or carboxylate is actually a relatively strong conjugate base, in which the lone pair on O is able to deprotonate some of the H3O plus ions, and as a result, give back or form back water molecules and form back some of the weak acid. And now let's focus on the right hand side of the slide. Our conjugate base in this case is chloride anion, and a chloride anion is actually a very relatively stable base. It is not really that basic, and its lone pair will not be able to perform the same way as what ethanoate did in the previous slide. So as a result, it is unable to deprotonate H3O plus ions to form back HCl. Hence, when we compare side to side the concentration of the H plus ions in both beakers, we can see is the left hand side, which is the weak acid, that has a much lower concentration of H plus ions as compared to that of the beaker with the strong acid. And that precisely gives the definition of what makes a weak acid, and what makes a strong acid. But now let us review actually what can we learn from this inquiry. We have seen that for the forward reactions, the both weak and strong acid actually does the same thing of playing the role of a broadside acid. And thus, what is the differentiating factor between a strong acid and a weak acid is actually the strength of the conjugate base. To recap, it was the strong conjugate base of ethanoic acid which is able to deprotonate a H3O plus ion to form back some of the ethanoic acid and some H2O molecules, which thus decreases the concentration of H3O plus ions or H plus ions inside the left beaker. Well, for the right beaker, it was the weak conjugate base of HCl, the chloride ion, that was unable to do so, which helped to preserve the high concentration of H3O plus ions. Although definitely this is not the most accurate representation, as you know that firstly there are just a few molecules, and secondly for equilibrium reaction the forward and backward reaction are constantly happening, but we can derive how to answer the first question, which is that a strong acid is strong due to the weak conjugate's inability to reprotonate. As for the weak acid, the reason why weak acid can have dissociate to give such a low concentration of H plus ion is due to the strong conjugate base ability to deprotonate or reprotonate and form back weak acid, and also deprotonate to decrease the concentration of H3O plus ions. Likewise, in a similar vein, when we compare the strength of a weak base or strong base, we can also derive this relationship of a strong base weak conjugate acid and a weak base strong conjugate acid kind of relationship. And what can we derive, or how can this information be useful for us in the later part of the topic? We realize that the conjugate base ability to whether conjugate base or conjugate acid's ability to uh, deprotonate or protonate a H2O molecule will determine whether a salt can be acidic or alkaline when dissolved in water.